Benvenuti, do un saluto come coordinatore del dottorato al professore Banchi, che ringrazio doppiamente per aver accettato con un preavviso praticamente nullo questo nostro invito, intercettato dal prof. Falci, che ringrazio altresì, e lascio immediatamente la parola, come da prassi, a un nostro dottorando, come dicevo al professore Banchi, di fresco arruolamento, per dire, no? Perché del nuovo corso. A voi la parola e buon lavoro.
Good afternoon, everyone. I will speak English since there are non-Italian speakers in the audience. So I welcome you to this seminar, which is part of the Highlights in Frontier Physics. Today we have the pleasure of hosting Professor Leonardo Banchi, currently Associate Professor at the University of Florence. I will give now a very brief presentation about Professor Banchi. So he, for his PhD thesis, he won the Fubini Prize by INFN, and then he went on to cover various research roles in international institutions, such as the Imperial College and University College London, and then the quantum computing company Zanavi in Toronto. And then in 2019, he won the Vitale di Montalcini Fellowship and has been at the University of Florence since then. He has also taken part in national and European projects and initiatives such as the NQS-TI, and his research focuses mainly on quantum computing and quantum information, with particular attention to quantum many-body theory, quantum machine learning, and so forth. So we are very pleased to listen to the seminar about quantifying the complexity of learning quantum features. Thank you.
Thank you for the presentation. Thank you all for being here. So indeed, in this talk, I will speak about quantifying the complexity of learning quantum features, and I will give you a very brief idea of, let's say, the main idea behind this talk. So the main idea behind this talk can be exemplified in this picture. So you have some classical input, where here by classical input can be anything. So either you are doing quantum machine learning and then the input is something that you want to classify using your quantum computer, or it can be some classical parameter in your experiment, like a magnetic field or something that you can control in the experiment. So this is actually, so this classical parameter is embedded into a quantum state. But this quantum state not only depends on this classical input, it also depends on some other hidden quantity, which is this y, that I will call from now on feature. And the idea here is for all the possible x, I want to extract the corresponding y. Okay, so this is for now very abstract. And I will tell you, let's say, what kind of problems can be rephrased in this language. The whole point is that by varying x, so we can explore different states. So that's the whole point. And what we want to do is that we want also to be able to extract the feature y in some way. So for instance, with some measure. So let me tell you some examples. So if you are coming from quantum many-body physics, so a standard example that can be rephrased in this language is the idea of classifying phases of matter. So the input x here is the set of external parameters. So your parameters in the Hamiltonian. So rho of x, if you are interested in quantum phase transitions or phases at zero temperature, is the ground state of a certain many-body model. And then, so y, which is the parameter that you want to extract, which is somehow encoded in a complicated way in the ground state, is basically the phase of matter. So whether it's paramagnetic, topological, and so forth. And so here the idea is can be also to reconstruct the whole phase diagram. So you don't care about what to measure, but you only care about a picture like this. Or if you are talking with experimentalists, you also want to tell them how to reconstruct this phase diagram in experiments, and so what kind of quantity you have to measure. Okay. Now, other ideas that can be written in this language, and I will tell you also, let's say, various possibilities in this talk. So one is the general quantum state classification. So for instance, you have a bunch of states, some states that are, I don't know, separable, some other states that are entangled, and you want to find a measurement that tells you whether this class of state, that particular state is entangled or not. Or quantum machine learning. So quantum machine learning normally is the idea of using a quantum device to classify classical data. So you have some classical data, like some image of a cat. Then this arrow here is the quantum embedding. So you embed this classical image into a quantum state via some parametric quantum circuit that depends on the image itself. And then you do some measurement at the end. And you want to optimize the whole thing in order to be able to classify whether this is a cat or a dog or whatever. Okay. So that's somehow the idea in quantum machine learning, and then again can be rephrased in this language here. Now, the third possibility is if you are, on the other hand, more focused on quantum sensing, where the idea is to devise sensors. And in this approach here, what we were doing in this bunch of papers was to imagine the problem of classifying handwritten digits, but with a quantum sensor. So here the idea is that you have a quantum sensor, I don't know, some squeezed state of light that is injected into some sample, like a charted line written in the wall. So you are using your scanner, like your quantum light. Some photons are scattered back to the detector, and based on what the detector see, you want to understand what is the pattern in this image. Okay. So of course you can do single pixel sensing and then use a classical post-processing algorithm. But what we found in this series of papers is that there are more clever ways to exploit quantum features. I mean here like entanglement, squeezing, and so on. So in this language, so the X would be the pattern. So the X would be like the image which lives in the physical world. Rho will be the state which is represents what are the photons collected by the detector, and the Y is how do you measure this state in order to extract, for instance, whether you have a 9 or something else. Okay, again, everything can be rephrased in this kind of language. And then, of course, here we are within the setting of learning with quantum data. And by quantum data, we mean something which lives in the quantum space. And of course, everything is more complicated because quantum data cannot be copied, so you have to repeat the measurement, and so there is also a measurement overhead that must be taken into account. So here we have a review where we somehow cover all the complications in dealing with quantum data. And so for instance, if you're interested in device characterization, like learning quantum states without doing tomography, quantum dynamics, or quantum measurements, so here we give an overview of what are the main techniques. And but let's get back to the main topic of this particular talk. As I said, we have this mapping, so classical input, set of states, classical output, and we might want to learn two particular things. Either we don't care about this, so we only care about this particular arrow, or we care about this. So in this case, so for instance, in this thing on the top, so this is, for instance, the setting in most quantum machine learning algorithms. So you don't care about how the cat is represented as a quantum state. You only care about recognizing a cat in a classical image. So you only care about this direction over here. While if you want to classify pieces of matter, you are more interested in this direction because you want to tell the experimentalist what kind of quantity you have to measure. And so that's here, for instance, the example. So if there is one point in the phase space in the diagram, so you might not care about also what is the measurement to perform. You only want to care about what color should be this point over here, and that would be understanding this arrow here. If you want to tell the experimenters what to measure, then you are interested in this arrow. Now let's try to see how we can define a complexity of this kind of process. Now, and I will introduce this not via some mathematics. Of course, everything here can be made more formal, but I will try to tell you this idea via some examples. So, in the first idea is that of dealing with classical machine learning or quantum machine learning with classical data. Again, here we don't care about this intermediate representation. That's a trick that we do in the algorithm, hoping to get some quantum advantage, but the whole process that we care about is only this. So here, everything is basically classical. There is nothing quantum rather than the model, but that from the statistical complexity point of view, this is just a classical problem. And so one can use the tricks that are known from statistical learning theory. And in statistical learning theory, if you use, for instance, the supervised learning approach, where you train a model with a bunch of known data. So for here you have a labeled data like images, and you know that these images show some cats are shown. So you train the model, and then you test the model to see whether this new image represents a cat or not a cat. So there are generalization bounds, where by generalization we mean that we train the model with some images, and we test the model with some other image that it does not belong in the training set. So the model generalizes whether if it's able to go beyond the images used during training, and also test something which is different. So this generalization error from statistical learning theory, so this is the error here, basically it's known that it behaves as a certain quantity, B, divided by n, and here is the number of training samples. So here we can say that the complexity of this process is basically the B, because as long as the number of training data is much bigger than this quantity, then you know that somehow the model generalizes and you're happy. Now another example, this time is a quantum example, but we don't have the X. So we have just a bunch of states that depend on some classical variable y, and you want to extract the y. So this is the standard setting in quantum sensing, especially when the y is a continuous quantity, or quantum hypothesis testing when y is discrete. And in quantum sensing or hypothesis testing, we know that somehow the complexity is given by the sample complexity. And by sample complexity, I mean the number of copies of the state that you have to make in order to be able to extract the y according to a given decision. And of course, here what we want to learn is the measurement. So what kind of measurement you have to do in order to extract the y. So, and there are different possibilities. So for instance, when y is continuous, like in metrology, so the error is normally quantified as the mean square error, which is basically an L2 loss. And normally this error behaves as the number of samples, so the number of copies, the -1. But using some quantum tricks, you can also get the Heisenberg limit in some cases and also achieve better scaling like this S2-2. So this is when y is continuous. When y is discrete, then normally the error is, so suppose, for instance, in the case where you only have two possible values, like, so then the error is the probability of getting the wrong value, so the probability of misclassification. And again, using some information theory, you can bound this quantity using some entropy, and here is the mean entropy. And analyzing this quantity, you see that somehow this always decreases exponentially with the number of copies. And again, if you use some quantum tricks here, well, the advantage is that you get a better exposure. So the error can still go down more quickly when you have, if you're using quantum tricks. But here again, we are in this simplified setting where there is no X. So what we were studying was what happens when we are in this more general framework. So we have an X and we want to extract a Y, but for all the possible X. So, and here we have, let's say, two notions of complexity. So one is, so to speak, the copy complexity or the sample complexity, namely how many copies of each state do we need? And that could be like the measurement shots if you're doing experiment in a quantum hardware. But and that would be like the quantum version of so how many copies are sufficient in order to generalize, in order to train the model and test the model. But we also have like a problem that we need to see many of these examples, like in the example with the cat. And so we need to also ask ourselves how many values of n of x do we need? So how many images of cat do we need to use to teach the quantum model that this is a cat? And clearly now we expect that the error is a function of both the n, which is the number of x, and s, which is the number of copies of this state that we have to prepare. And I have to say that nobody knows the answer. So nobody knows what is the ultimate limit for this particular dependence. But what we have done in this paper, we have shown that somehow using some quantum algorithms, one can jump from a complexity that depends on the dimension of the hyperspace and a complexity that does not. So one possibility is that, okay, so first you do some tomography with some precision, and then you do, well, once you have done tomography, then you have basically classical data. So, and then you can apply classical tricks, and then you get to this bound. So this bound is bad because there is this D, which is the dimension of the Hilbert space. So you have a dependence, which is ns to the minus 1, 2. But if you have like a multi-qubit system, this D grows exponentially. And so you need an exponential number of data to But what we have shown is that if you do some quantum tricks, and the quantum tricks is that you exploit parallelism, so to speak. So you put all the training data in some state, you put some test state in some other state, and if you do like a quantum algorithm here, which is based on for those that know quantum algorithms, this is basically a combination of the quantum state exponentiation algorithm, which is at the heart of quantum principal component analysis or other things, and more standard phase estimation algorithm. Okay, so by combining these two, then you end up with an algorithm with a bound that has a worse dependent on n and s because it's 1/3 rather than 1/2. But at least you remove this dependence on d. So this, I mean, it's not going to be simple because you need a very big quantum computer, but you can claim an exponential advantage because here you don't have this dependence over D. And this is very general, okay? It does not depend on the problem. It only depends on, so it can be defined in this way for every possible problem. But it's very hard. Okay, it is not. You cannot phone your favorite experimentalist and tell him to do this kind of experiment because it's very tricky. So, so what we would like to understand is that is how can we do something without something which is still efficient, but without having to use algorithms like this. So the idea is that, so what we know is that it's possible to avoid the exponential complexity, but the price to pay is that we have to coherently manipulate all of these states. And the task now is to understand whether we can avoid this at all and still learn some problem efficiently. And so the idea here is to understand what kind of problems are easy or complex to learn from data without having to resort to, I don't know, things like this. Okay. Okay, so maybe this go quickly, but just to tell you, so we are working with a single copy framework. So what we do is that we either take a measurement on the state and then process the outcome, or we do multiple measurements and we process the average value on observable. So in this language, we are dealing with generalized measurements like POVMs. So we take a measurement, and from the output of this measurement, we extract a feature. So the task is to basically learn the POVM. Okay. The other possibility is that you have an observable that tells you the outcome. And so here the idea is that you measure the expectation value of an observable, and from the expectation value of such an observable, you make your decision. Okay, so we are working with these two frameworks. And so what we have done with these two frameworks back in 2021 is that by studying somehow the complexity of this state space, then we realized that somehow the errors behave in two ways. So first of all, there is this bias error, which is the ultimate error that you can achieve, assuming that you know everything. So you know the probability distribution of caps, okay, which is clearly not possible. But assuming that you know the probability of the underlying data and you assume also the quantum states, that's the ultimate limit you can achieve, which is basically due to bias theorem. Then what you do is that you train the model. And when you train the model with some examples, the more complexity, for instance, the more parameters you add, the more training, the more expressive the model is. And so the training error, which is this red curve, goes to 0. And this training, the difference between the training error and the ultimate, let's say, error, basically can be quantified using information theoretic quantities as the mutual information between the y variable, so the classical feature, and q, which is the set of quantum states. So this is known, okay? It's just rephrasing known results about hypothesis testing, quantum hypothesis testing. What we studied then was to happen to the generalization error. So you use the model that you train here, but then you test it with some new images of caps, for instance. And here, the error is this generalization error, and somehow the new result in this paper is the generalization error decreases as the square root of the number of training data, as we know from statistical learning theory. But the abstract quantity that was here now has a physical meaning, which is the mutual information between the space of classical inputs and the quantum space. So this two is because it's a really mutual information, but that's just a point. I don't want to go much into that. So what's the idea here? The idea here is that assuming that each color, so this is like a Hilbert space, each color defines a feature. So, and while different points have a different x. So if you think that in your Hilbert space, the data are clustered, like all the green points are in some place, all the red points are in some other place, then in this language, we have a large mutual information between the feature and the state, but a small mutual information between the classical parameter and Q. So they are kind of clustered, this data. So whenever we have something like this, then efficient learning is possible because you can always find, I don't know, some decision plane, which is an observable, capable of separating this data. So this was for us the driving principle.
I understand that Y and Q are, of course, connected with a cluster, but then is X related to some distance between the dots?
No, actually, the X is just this framework. So this is the Q, this is the X. So I think the easiest thing is to see with an example. So in an example, X is the classical parameters of a Hamiltonian. This is the ground state, and this is the phase of matter.
Yeah, okay.
So if by changing your parameters, you move in the Hilbert space, but not that much.
Okay.
And when you change the phase, then you are far away.
So in a sense, in this example, X is the
is
the distance between the small dots.
the kind of yes, exactly. And when you have a phase transition, that's somehow the distance increases. But that was also the starting the motivation for us.
Just the drawing, you can say, okay, green, I'm in a phase.
But this is a very cartoon picture. Okay,
Yes,
it's just yes.
It's nice to have.
Yes, exactly. So that was for us. Okay, so maybe this is more for people doing quantum machine learning. So these quantities can be computed using again some entropies, but I won't go into this detail. If you are interested, I can tell you later. And so using this framework, then we can say that classifying quantum phases, or at least some, okay, I'm not claiming all quantum, but some quantum phases of matter is easy, and I can tell you why. So in this setting about the phases of matter, again, X is the set of classical Hamiltonian parameters, like magnetic fields in your Hamiltonian, couplings, and so forth. Rho is the ground state, and Y is the phase, which is what we want to extract. Now, why do we care about learning in this setting? So the main assumption for our study is that suppose that we know the phase diagram in a subpart of the parameter space, either because numerical methods, your favorite numerical method work well, like tensor network, quantum Monte Carlo, or whatever. Then what you do is that you use the knowledge from where you can trust your numerical method to train a model, and then you let the model to decide what to do in the other space. Okay, so that was somehow the idea. Now, of course, we tested. I think this is a technical point. I will skip this slide, but just to show that somehow we were using a framework which is based on support vector machines, which are basically hyperplane, and we are studying hyperplane in the space of density matrices. But that's a technical point, and let me go directly to the. Okay, yes. So then we tested this model using some spin chain model. So here we are in one dimension. We have a ferromagnetic interaction between nearest neighbor, anti-ferromagnetic interaction between next nearest neighbor. So you have a kind of frustration. That's why economic model is interesting, but in the same direction. And then you have also magnetic field in another axis, which kind of complicates the matter. So this is the one-dimensional axial nearest neighbor Ising model, which has a particularly complex phase diagram with a ferromagnetic interaction when both K and this is an H, even though it's a bit hidden here, when both K and H are small, so when these two terms are small. So then you have this anti-phase, which is kind of anti-ferromagnetic, but between nearest neighbor. Sorry, next nearest neighbor, which is when this is the dominant term. And then you have the paramagnet when somehow H is the dominant. And then in the middle, there are also some Kosterlitz-Thales transitions. And so it's a complicated model. So what we...
This is not, this does not conserve the number of excitations.
In the you mean the Jordan-Wigner language? In the Jordan-Wigner language, this is not quadratic. So does it conserve the number of excitations? No, because so even this does not conserve. So
the first one does not conserve.
Yes, it conserves the parity.
They conserve the parity.
I think even this one conserves the parity.
It should be good because it's sequence.
Yeah, so exactly.
Where you don't care.
Yes, I think even the most general one conserves the parity, but we cannot use Jordan-Wigner or fermialization techniques to analyze it. And so here we were using tensor methods. And you see that somehow, even though we deliberately trained the model with bad data, namely that we were using a very small bond dimension, so something like 20. Okay. Because we wanted to mimic somehow the errors if we try to do an experiment, we were saying let's try to get. So machine learning is particularly powerful even when you give the machine learning noisy data. So for us, the noisy data were the small bond dimension. Okay. So even though we were training with very bad data, so the model was capable of populating the phase diagram, and also something which was quite nice is that even so here we were training along these x directions, and so perhaps it's not particularly surprising that somehow the model populates everything because it's kind of just interpolating the points in the middle. But what was more interesting is that suppose that now we train only along these lines. So clearly you need to train a model where in some place where somehow you can use all the possible phases. So in this line, we cross all the possible phases, and then the model was still able to generalize and extract and be able to classify the phases of matter also in the other form.
Sorry, the white spot means that it is unable to classify, or it's able to classify the floating.
It's able to classify the floating phase, yes. And of course, so here I think it was 50 spins. So there are big finite side effects, and the floating phases are Costa-Rica. So this is a Costa-Rica transition. So I mean, it's clear that getting this is quite hard. Okay. So this is something that we did mostly last year. This has been published this year. And I didn't have the time to put a new slide, but this week we also, maybe even yesterday, we submitted a new paper where we study these models using unsupervised learning. So not supervised.
Quite the other question.
Yes, and actually it performs better, okay? So we were actually even a bit surprised that the model performs better if you just give a bunch of data and tell the model to, I don't know, find the phases, even the number of phases. Okay, so we didn't even tell you have to look for 4 phases. Okay, we simply gave the data, and the model was still able to classify this data and find the phases. So you can check the recent paper by Merlan, is still the first author, where we also discussed this unsupervised learning. Now, why we claim that somehow this is efficient? Because we were.
Which model do you use? Both supervised and unsupervised?
So we were using this model, which is the only model.
No, the machine learning model.
Okay, so so the machine learning model is, I can tell you from here. Now let me go back a little bit. So the machine learning model is this. It's based on support vector machines. So support vector machines, they are linear decision models which basically perform a linear discrimination in the feature space. So the feature space for us is the space of density matrices. Why? Because a hyperplane in the space of density matrices is an observable. There's a measurable quantity. Okay, so that's why somehow we were using this space of this feature space of density matrices, because the hyperplane in the language of support vector machine is a measurement. So you measure an observable, and from the sign of this observable, you find the phases when there are 2 phases. When there are more than 2, it's slightly more complicated. You train basically different classifiers, and then somehow the model combines this into a final.
Classical machine learning model.
No, it's so this is the framework. Now there are some theorems that basically, which is the representative theorem, which basically tell you that the optimal decision hyperplane is a linear combination of the training states, which are this row of x of n. So the optimal. So then, if you want to test a new state, you want to somehow be able to measure this observable, which is a linear combination of the training density matrices on a device. Now, how do you do that? The idea is that now you have to. So clearly, if you expand, if you put this into here, the only thing that you need to be able to measure, either classically or in a quantum device, is what is called the kernel, which is basically the fidelity. Okay. Now the fidelity can be for instance, we were using tensor networks. So for tensor networks, the fidelity can be evaluated using a complexity which is linear in the number of spins, so which is efficient. And this quantity can also be estimated experimentally via swap tests, Hadamard tests, and other tricks. Okay. So even everything that I'm saying can be also done in a quantum experiment. And again, this is the training process, which basically involves solving a convex optimization problem. And this is somehow how we can. So there was a paper last year, I think it's published something. It's not so surprising. I mean, this guy's always publishing some Nature something. But anyway, so here they have a way to basically measure the fidelity using some tricks coming from shadow tomography, and they show that somehow this can be done efficiently. The other possibility that comes from the fact that our training states are computed using tensor networks is that one can map a tensor network state such as an MPS into a parametric quantum circuit. So now we can also apply the parametric quantum circuit back, measuring the computational basis, and that tells you the curve. Okay. So there are these two possible ways, so either using techniques from shadow tomography or using this mapping from tensor networks to parametric circuits in order to obtain the measurable quantities directly in the hardware. And finally, so putting all the theory together, so the prediction is now given by the sign of this observable quantity. And the observable quantity is written as a linear combination of the schedules. So now the whole thing can be efficient if we can bound the number of this n. So how many training states do we need? And so here we are using this complexity bounds and a mixture of theory and numerics. Let's say by putting together everything, we were showing that somehow this numerically, at least numerically, grows linearly in the number of spins. So we claim that somehow the complexity is not exponential in the number of spins, and so that somehow everything is efficient, at least for this particular model. Then we also tested another model, which is a one-dimensional Haldane model, which is again a bit complicated. So here's this extra three-body term, x, z, x. Then you have again a nearest neighbor interaction in the z, and then you have a field. So this model again is complicated because it has also a topological phase in the middle. And again, here we were training only along a particular line, and somehow it was able to extract, to generalize, and find, not perfectly, but I would say reasonably well, the rest of the field. And again, this model has been tested using unsupervised learning. So if you're interested, you can find the paper online. Let me see, how much time do I have? How much time do I have?
You're the chairman.
I think 2 hours.
2 hours?
You think
It wasn't. I wasn't told the exact amount of time.
usually
2 hours, the audience will start shooting me, you know, or
usually
I mean, I have enough slides perhaps for 2 hours really, but I think the audience is not.
Tell me at which point we are, and I will tell how much. And I will tell you.
I think we started. I think it's 40 minutes. It's for 40 minutes, roughly.
So you have at least or at most 10 minutes.
10 minutes. Okay, that's
So no, you have to say.
Okay. So we have at most 10 minutes.
I understand. Thank you.
At least or at most.
It's an upper bound or a lower bound?
It's both. We are very
It's
precise.
both.
I mean, with in Sicily we are just like
Yes.
much better than Switzerland.
Exactly. Anyway, so then let me briefly. So I have several other things that can be mapped into this framework, but I think the one that like perhaps the most is this out-of-distribution generalization. And the reason for us to study out-of-distribution generalization was again motivated by what I was showing here. Because, okay, so this is kind of in-distribution generalization. So it's an interpolation problem. So you train uniformly in the space, and then you see basically what happens in the middle. This is an out-of-distribution problem, because you only train on a very specific part, and you want to generalize far beyond the training example. So we wanted to understand a bit more the theory in this case. And doing theory out of distribution is quite complicated. And I will tell you why using some examples. And okay, so first of all, some reference. Most of what I'm telling you is the work by Jason that used to be in Florence, and now is in Paris, and has been again published a couple of last month. And so let me tell you what we mean by in-distribution and out-of-distribution. So in-distribution generalization is when you train a model with some labeled example, as I told you before, and you want to test the model with something new. So you train with cat images, and you want to test the model with a new image, different from the training set, but within the same distribution. Now, clearly, this is very abstract. What is the distribution of cats? Okay. But mathematically, you assume that even the test datum, the test cat, is from the same distribution of the space of cats. Okay. Now, let me tell you something a bit more tricky. So suppose now that you are training the model only with gray cats and brown dogs. Okay. And now you ask the model, you feed the model with a brown cat. And you ask the model, is it a cat or a dog, right? So this is now more tricky because either the model has learned that a cat is some animal with this shape, and then the answer is a cat. But if the model is dumb and only thinks that somehow a cat is some gray animal and the dog is some brown animal, then this is clearly a dog. Okay, so that's why somehow this out of distribution is quite complicated. And one can find examples where somehow the theory tells you that this is included, okay? But so this out-of-distribution generalization basically requires the model to learn these two underlying features rather than what in the language of machine learning are called spurious correlations. So they are these deceptive features that are highly correlated with the training data, but not with the true model. Okay? It's a kind of finite data effect in some sense. And so, for instance, if we are in a regression model and you train the model here, and then you predict somehow if the true model is something like this, and but then you use a very simple line, then you see that somehow this is very, very far away. And so we know that extrapolation is very complicated. And we know from fact, right, like predicting the weather, it's hard. Predicting the stock market, it's hard, right? So we know that somehow this is a complicated model. But what we have shown is that if we map this into a framework of continuous variable quantum information, this is actually possible. Okay. So here we are starting with this process where somehow we have some probe state, a continuous variable quantum channel, and we want to learn this. Now we get it without getting much into the math. We okay, maybe let me skip these definitions and let me go back here. So this is the central result. So what we have shown is that we can train the model using states, so probe states that are low energy. And we assume that somehow within this low energy space, the model performs really well, pretty well, so generalizes well. And we know how to get these small numbers because we know this statistical complexity bound that they behave as the number of training data that the model is one half. So we assume that we have enough data to know this channel in the low energy part. And then what we have shown is that using some tricks from quantum optics, knowledge in this low energy part allows you to extrapolate in the high energy part, still in the space of coherent space of high energy. And then once you extrapolate within the space of high energy coherent states, you can also extrapolate in the space of very non-classical states like Fock states and squeeze states and so forth. Okay. Now the math, I will skip the math because it's late, but somehow I want to give you the idea, okay, and then I'll stop. So the idea is that first of all, quantum mechanics is linear. It's clearly this. No. Okay, so that's not the intuition why everything works here, and I can tell you that with a very particular example. So suppose that, for instance, the low energy states and the high energy states they live in different parts of the hyperspace. Then clearly, if your probe state only lives here, you can only get a particular block of your channel, right? There is no way that you can get this information. So, and this is a linear problem. So this is not the right intuition. So linearity is not the reason why this works. So the reason why it works is actually a little bit more subtle. Is because so these low energy coherent states, they generate everything. So indeed, you can also arbitrary Fock states can also be written as a coherent mixture of low energy coherent states. So basically, what I'm telling you is that this doesn't happen. So even in the space of low energy, even using low energy coherent states, you still have some knowledge of the high energy part.
Because the basis is over.
Exactly. So it's mostly the over completeness of the basis is the key ingredient, not the linearity.
That's something to do with the wavelength response.
Possibly, I don't know. To be honest, I've never applied wavelet transform in anything, so I don't know much about it.
That day I was pronounced it.
Okay, and for me to hear. Yes. Anyway, and then of course the math can be ugly, and there are of course bounds and errors, but anything. So I will skip this part. And then again, I was also, as I said, I can speak for 2 hours, but indeed, I mean, with respect to everybody, let's cut this part. I mean, very quickly, classifying physics of matter is simple. Classify entanglement is not simple. And then I would also study some temporal processes like predicting stock market. I still haven't been able to make any money, so then so work in progress. But anyway, then some other stuff.
Then sell it to somebody
That's the problem, maybe. Yes. Yeah. Anyway, so let me jump to the conclusions. Extracting global features from quantum space is complex, but it can be done efficiently in some cases, like this learning of physics of matter. So the whole idea, the driving principle for us is that discarding information, so learning is good when you know how to discard the irrelevant information from the input that is not useful. The tricky part is that you don't know what's relevant and what's irrelevant. And then some classical data can be better compressed. So this I haven't, that was the part about the temporal processes that I haven't had time to speak. And somehow the measurement error can be also the dominant source of error. That's what happened, the bad part in the entanglement. And then this one I haven't said, but the non-orthogonality of quantum probes can also be exploited to learn quantum operations with the low energy states and still be able to extrapolate. And this again is due to the over completeness of coherent states. Okay. And with this, I thank you for your attention.